We introduced INTELLECT-2, the first global distributed reinforcement learning, 32 billion traditional reasoning model using fully asynchronous RL using dynamic heterogeneous swarm of permissionless compute contributors. We built various components from scratch. We introduced PrimeRL, our training framework purposely built for distributed asynchronous reinforcement learning. Novel toplock, which verifies rollouts from untrusted inference workers. And shortcast. So what does this mean? So we have these reinforcement learning techniques for training, post-training language models, and they're saying like we want to train them in a distributed way across many different GPUs, many different locations. So what do we need to do? We need to somehow take the model and give them questions and complete trajectories that explain the reasoning. And then we also need to manage like which nodes get which questions, how do they roll out, and how do we verify that a specific node generates the right thing. So for example, let's say Bob is part of this training run and Bob is kind of malicious. He says he's gonna use the R1 DeepSeek model to generate a trajectory for a specific math question, but he just makes it using some super shitty language model. And this would be bad because then it's influencing the training code, or maybe he's even trying to inject some malicious thing where he says he tries to make the reasoning trace wrong or something, which would mess up the training of the model. So that's what they're saying, that there needs to be some kind of verification of the rollouts, where the rollouts are the attempted solutions from the language model. And then shortcast, which efficiently broadcasts policy weights from training nodes to inference workers. So imagine that you have a distributed system where you have some nodes that are just running these models. They get some weights for the model, and then they generate some trajectories, some rollouts. And in that case, you would want to do, in the case where you're training in like this kind of online way, where you are not just generating the rollouts from a single model, but iteratively you're training and updating the model, and then you are generating more rollouts and so on. In that case, you would want to know like how should we coordinate which weights people have and how. So maybe there is some kind of central server that is managing this, like it's getting the rollouts from some inference nodes, and then this is what they call inference workers. These are the ones generating the rollouts, and then there are the training nodes, which would then be using these rollouts and training them using, for example, GRPO. So it says, beyond infrastructure components, we propose modification to the standard GRPO training recipe and data filtering techniques that are crucial to achieve training stability, thus improving upon Qwen Q32B. We open source INTELLECT-2 along with all of our code. So let's go. Test time compute scaling with reinforcement learning has emerged. However, reinforcement learning is typically decentralized, requiring large clusters. In this paper, we present the first large-scale experiment to collaboratively train a 32 billion parameter language model. Intellect, we open source it. We have PrimeRL, the first fully asynchronous reinforcement learning framework. Decoupling the rollout generation, model training, weight broadcasting. So rollout generation was the workers, their inference workers. The model training is using the rollouts with some algorithm, and weight broadcasting is sharing the weights after they've been updated to the inference workers. And this is then working on reliable networks. So you could imagine some inference workers, they're like not so reliable. They come and go. They have a computer where the connection is not working so well, or they just like the computer just stops working. And unreliable networks, maybe sometimes just the connection, even though the inference worker itself is reliable. And then you have the shardcast, a library for distributing large files via HTTP-based tree topology network. So that's for getting the weights to the inference workers. And then there's toplock, a locality-sensitive hashing scheme for efficient verifiable inference. So we need to somehow see that the trajectory, the rollout that we generated was right. So you could imagine doing something about some activations within the model or something, and then do some kind of hashing, but that is like locality sensitive, and say, okay, this trajectory could not have been generated so well from this. So protocol testnet provides an infrastructure to aggregate and coordinate global compute resources. Yeah, so there needs to be some kind of way for them to coordinate, maybe. The structure on 3 primary roles. By leveraging asynchronous reinforcement learning, the broadcast of new policy weights is fully overlapped with ongoing inference. Yeah, so here you see it. These are the workers. They have gotten some weights and they generate some rollouts for some questions, some math questions or something. Then when they're done, they send it over here, and these people, they will verify it. They will verify that indeed the thing is as it should be. They're not faking it. And then they're sending it over to the workers, and these training workers can then try to change the parameters in such a way that they get more reward based on this data, and then they say, okay, we're ready for using something else now. So we develop a new framework, training. To reduce GPU memory requirements during training, we shard the model weights, gradients, and optimize the states across GPU using PyTorch's fully sharded data parallel 2, following a strategy similar to 0.3, which is a training library, I believe. We load training data from remote storage, and rollout data is exchanged between inference workers. So there needs to be some kind of third party up here, fourth party, that just has the data for the questions at least. Rollout generation is transferred to the trainer as we compute log probability using the policy at the start of the optimization step. So the asynchronous of the rollout generation is transparent to the trainer. So you could either say, I'm having some trajectories, and if you were like fully like online in a sense, you would say, I care about the policy that generated these things, these trajectories, and now I'm going to look at the likelihood that it has assigned to it, and then I'm just gonna update with respect to that. But they're saying, no, actually we are gonna use some policy, and this policy we're training now, we're gonna of course look at the log probabilities of and change the log probabilities, but it might not be the ones that produced the original trajectories, probably because it's asynchronous like that. but whirl is probably not asynchronous. In its current form, Prime implements GPO along with auxiliary KL and entropy losses. To generate the rollouts, we use VLM, loading the model in bfloat 16 precision. For each batch input, questions are sampled randomly using deterministic seed from selecting easy samples. Input questions are sampled. To support top-log proof construction, we capture the final hidden states. Yeah, so let's imagine you're like generating all the tokens for your rollout. Then at the final hidden states, you either the logits or like the state before. These are some vectors, right? One vector for each token, and you want somehow to say, oh, these are the result of using a specific transformer model with the specific weights that they're supposed to use for rolling out. And instead of storing the activation of the full sequence, we incrementally store and hash them at every 32 token interval, which reduces the memory overhead. So you just take every 32 tokens and look at the vector associated with that in the last layer, in the final hidden states. And then you have some bytes. So maybe you have a 1000-dimensional vector. Then you can use some kind of hashing function. You turn it down to fewer bytes. And then you save all this, and this will be some kind of proof that you used this model with this to generate it like this, because it would be very hard to fake that. And to reduce blocking overhead, the proof construction is performed asynchronously on the CPU in parallel with the GPU forward pass. How can you do that? Well, because the rollout is linear in time, like you are generating one token at a time, then you can also, while you do this every 32 times, you can kind of do the CPU stuff. Together, these optimizations limit the overhead of proof generation to only a 1% reduction in tokens per second throughput. To keep the inference workers in sync with the rest of the training, we host a step counter endpoint, which returns the smallest step with insufficient rollouts. So imagine you're trying to coordinate, and you have in way decided already before you start the whole run how well you which kind of questions you want to have rollouts for at which points. So then the workers, the inference workers, can kind of just rely on some kind of global reference. And if you had some kind of step counter endpoint, then you can kind of say, like, where are we actually? Which do we need? We ask the step counter endpoint, okay, we're at step 70, and at step 70 we need to have more rollouts, and probably steps here means the gradient step. So you could imagine that there is then a number of gradient updates from the GPU trainers, and they're saying, like, now we need to do this. So if a worker is kind of doing something else, then it needs to maybe make sure it has the right weights for step 70 or something, and then do some rollouts. And the rollouts will be then sampled using deterministic seed up here, and then it will say, these are the questions that we need to try now at this step. Inference workers pull this endpoint and generate rollouts. Yeah, this design allows workers to dynamically join or leave the computer without interrupting the training process, because if you just stop, then you're not responsible for anything in particular, maybe, because the only thing that we just need at all points is that at each step, which we have a global reference for, we will know what things we need, which questions, which training questions we need to solve, and therefore Prime RL uses Genesis schema introduced in Synthetic 1, making it easy to implement new reward environments. In our initial experiments, we support symbolic verifiers for mathematics and unit test execution for Python-based coding and competition problems. For this, we adopt existing implementations from 21 and 8. Pretty radio. Pretty radio. What? Okay. Yeah, so of course, like you don't only have you have some data set you want to train on. And for now, I just said like maybe you have some questions and you could imagine they're mathematics questions, but they could also be that you're actually generating code and you want to check whether it works. So there we need to know where to look at whether the reasoning traces are good and so on. And maybe they say that the rewards are here. So that would indicate that actually the workers themselves are also running the reasoning traces and seeing if the code was, for example, compiling or whatever environment you're dealing with, then you need to do that. And that is the Genesis schema. LLM generated code is executed on the inference nodes where we already applied sandboxing and code sanitation. So that's what I just said. It's in inference nodes. At this point, the approach provides sufficient isolation for the simple algorithmic challenges currently used. For more complex coding tasks, further strengthening of isolation mechanisms, file system access, and so on. Shortcast. One of the key challenges in asynchronous distributed reinforcement learning is a decentralized setting. Is ensuring the most recent policy weights are quickly delivered to inference workers. Because you want to train very efficiently. So if we already solved step 8 and we're going to step 9 now, we need that all the inference workers down here, that they have the right weights and they need to get to that point well. And so that they can be ready to train for the next step. So how do we do that? For this, we utilize a network of relay servers that distribute the checkpoints from the main training service to the client inference worker, similar to content delivery network. To minimize latency, checkpoint files are sharded and streamed in a pipeline fashion, allowing inference workers to begin downloading shards before the full checkpoint. So imagine, you could just think of it maybe as the different layers of the transformer. It has different matrices inside, and you will then send it to some kind of relay, some intermediate point, and you're just sending one layer, then the next layer and next layer. But if you're pipelining it, then once one layer is available, fully reached here, it can go out to the inference workers here, bam, bam, bam. And in this way, you can start having them, and technically, but it's probably not worth doing, but you could even imagine like starting to run some basic forward pass on only some of the layers if you wanted, but that's not the point here. So the relay servers only keep the last 5 checkpoint versions to avoid running out of disk. So these servers will have to host the full model, which could be, depending on the model, it could be hundreds of gigabytes, and you have different checkpoints because you might not be fully done with the first step. I will still have to think about like, why is it that they do not always know which step they're at? Why do they need to keep 5? But they're at least keeping them, so they have to be quite big, these relay servers. and functional desirable as rollouts generated without its activity rejected or discarded. Yeah, so rate limiting, we use Nginx as our HTTP server due to its robustness and widespread industry adoption to protect the relay service from malicious inference workers who may make an excessive number of requests. We configure our Nginx server with IP per rate limiting. Additionally, we dynamically configure UFW. Firewall to rules and to receive traffic only from known currently active inference nodes in the compute pool. This reduces the surface area of attacks and enables to quickly blacklist misbehaving nodes. Yeah, so you could imagine that some other agent, malicious entity, tries to disrupt it by like using a lot of traffic and say, I want also these model weights that are stored in the relay, and therefore you don't have so much bandwidth and so on, and it would slow down. This would be one thing. You could also imagine other things, but maximizing client throughput and load balancing. If each client were to always select the fastest relay server, it would lead to contention and bandwidth thrashing. To mitigate this, clients instead sample from the set of server relays based on the expected throughput of requesting from each relay server. So that just means we want these inference servers to quickly access the new weights that they need to use for inferencing the rollouts. And which ones should they select? They should, of course, not just select from the same one. They should like distribute it well, and therefore they need some kind of mechanism to say, okay, this one is the one where I can have the shortest like expected time to get the weights that I need. Our implementation begins by having each client request a dummy file from all relay servers to initialize bandwidth and success rate estimates, then select in proportion to success rate times the bandwidth. So success rate, how often does it work? This is like the probability that I will get it, and this is the bandwidth. So this seems like a reasonable estimator of the expected throughput. And you can then imagine, so what does it mean? It means like this node down here, it will say like there's a little file, a text file, something. It will ask the different servers for this information, and it will ask it often so that it gets some kind of estimate of like the success, how often does it get it, and it will also estimate like how quickly it gets the file compared to how big it is, so the bandwidth, the bytes per second, and therefore if you then like continuously do this, like you often ask different files like this, servers, relays like this for this file, you have an estimate of the success, how like stable the connection is in a sense to this specific server, but it's not only the connection, it's also how like successful the server is in itself, because it might be overloaded by other inference workers. So therefore you kind of estimate like this kind of success thing, and if you then continue to do it, you can have like a moving average, so you smoothen it out a bit. And it's a smooth transient fluctuations. Yeah, a healing factor is incorporated to encourage periodic exploration of underutilized servers, ensuring the systems, even in scenarios without contention, the probabilistic sampling strategy outperforms greatly, choosing the currently fastest relay. Assembled model weights integrity checks. Inference nodes face a risk of being penalized if they submit rollouts generated using incorrect model weights. Why is this? Because we want to train. Remember, like the whole goal is that we should train it. And these trainers up here, they're saying we are at step 70. Before we used these weights, these parameters, now we want to get some new parameters. Therefore, the way that our training algorithm works is that we want inferences rollouts from a model with these parameters that we're thinking of. Therefore, these inference workers down here, they should be using the same ones. If they're using the wrong ones, then they will have some rollout, but the rollout will be from the wrong step in the training process. Therefore, when they send it somewhere, to the trainer, actually not to the trainer, they send it to the top lock validators. When they send it to the top lock validators, there will be a rejection because they cannot use it. So that's why it's important to do that. To avoid this, it is essential that only verified correct weights are used for inference. To ensure model weight integrity, each inference worker computes the SHA 256 checksum of the assembled checkpoint after downloading and reconstructing it from the shards. That just means when I am here and I'm getting the new weights from the relay, from the shardcast, then I will have to check that I got the right ones. And how can I do this? Well, it's just a bunch of bytes in essentially it's just a big file. So I can hash this file and have a unique fingerprint and just check that it is the right one if I can talk to someone who can verify for me that it is indeed that one, and that should be quite easy to do. This checksum is then compared against the reference checksum produced by the training nodes, which is broadcasted to all relay servers along with the checkpoint metadata. If the computed checksum does not match the expected value, the inference node discards the chart and proceeds to attempt download of the next available checkpoint. We avoid retrying the same checkpoint as it is unlikely to re-download would complete before the checkpoint becomes stale or irrelevant. While a mechanism for verifying the integrity of downloaded shards would enable trustless peer-to-peer weight transfers, while a mechanism for verifying the integrity of downloaded shards. Yeah, so you could imagine that they talk to each other down here and ask like, hey, do you agree that we're now like using these model weights that have this checkpoint, this hash? And it says yes, and everyone coordinates and they agree. But it's not that difficult because like it doesn't require a lot of resources to just like have some server that says what the actual ground truth for the checkpoint hash is. So that's a reason. But yes, but it could be nice because these inference workers here, they could then coordinate and say, but I'm missing something, just like in when you're torrenting something, then you can do that. But and then you would not need as much relay servers and everything, but that's actually quite interesting. In a P2P set, inference workers, if it would become visible to peers, requiring additional hardening to prevent the malicious behavior of denial of service attacks within the pool. What does that mean? Malicious behavior can be a lot of things. Denial of service attacks within the pool could just be somebody's like pretending to be a lot of different peers or something, and then they require all the time new weight from people, and this would like requires a lot of bandwidth and like not only bandwidth, but if this worker up here is getting a lot of requests to share one of its layers or something, then it will have to use processing power on that, and then it might fail. So or something about the bandwidth. It would just be using too much bandwidth to send all these layers, and then it cannot do send the layers to the ones that actually need it, for example. Given these concerns, we opted to centralize weight distribution through trusted relay service instead. So that's what they do. Top lock. So top lock was the idea that we need to make sure that actually the rollouts are right. Because we rely on trusted compute nodes for inference, there is no inherent guarantee for the inference nodes perform the inference faithfully. Validators use several checks: computation, sampling, and sanity check, which we will describe in depth in the following sections. I will just go back to this schema later. So, computation checks. Proof of correct model computation. As shown in figure 3, to confirm the inference was performed using the correct model weights, each inference worker generates a top lock proof. That's what we saw. It was the they didn't invent it. Okay. Maybe they did. Yes, these are those. this prime intellect, they are saying how you do it like that. And then that was the idea of every 32 tokens you take the hash of the hidden state in the last layer, and this proves to have a cryptographic commitment to the final hidden states during decoding. So that's what we often have in this cryptography. We say like you have some kind of commitment. This is what you need to share, and then you have some kind of proof that you can that like if they're committed to the wrong thing, like then they will be found out to be wrong or something. And then there's all this stuff with like soundness and completeness and so on. To the final hidden states producing during decoding, a trusted validator node subsequently reconstructs these activations using prefill and compares them to submitted commitments to confirm consistency. What does that mean? So when you're doing inference, you're generating one token at a time, and then you're getting all these hidden vectors and the rollouts and everything. That's all nice. It takes quite a lot of time, but you might have a hard time fully utilizing the whole GPU like that. Or if you do, it just might be like you cannot just do it at double speed very easily. But like if you have the whole sequence and you then make a forward pass in your transformer, then you can like compute the whole thing. You can compute the final states for the whole thing in one forward pass. Of course, like, you still use more computation than like just a single token generated when you have a KV cache, but you can do it faster in wall clock time, and therefore this is also the same thing that's used with speculative decoding, where you can also like use a smaller model. It will generate a lot of tokens, and then you just forward that through a bigger model and like check how they agree and how many tokens you can kind of use before you're moving. You just have to reject it and try again to use your small model. So it's if you have a trusted validator node, maybe they're down in the corner here. So if it was like some company, Prime Intellect company, maybe they hosted a training run for Intellect, then they would say, oh, we trust ourselves. So we will have some nodes down here, and they can also, of course, get the current weights and everything, and they can say like now we have the same weights for the model as the trainers should have had. So now we will indeed check if they were using the right model and they were not faking it or something, and then they don't need to generate token by token. They just use a full forward pass with the right model, and then they see, hey, let's do the top log hashing of the every 32 token hidden state and check whether they agree, and if they don't agree, there is something wrong. So that's the question is then, it says the proofs generated by top log are robust against GPU non-determinism because maybe the hashing is not just like a simple cryptographic hash of the bytes, but like is a locality sensitive hashing. Which means like, imagine for example you of course it's not the best hashing, but you could imagine taking the sum of the elements in a vector, right? That would be like a mapping from the vectors to something smaller that is easy to verify. And if you then have another GPU where there's something that's a bit weird about like how it sums together and stuff, so the forward pass will be a bit weird, then if you have the sum and it's still quite close, maybe the sum of one of the vectors was 3.2 and the other was 3.4, then it's close enough, and then you can say, I believe that you actually used this thing. Different tensor parallel configurations and are able to reliably detect when quantized or malicious versions of the model are used. So this would be one thing. Like, let's say somebody just wanted to be part of the run, but they used a quantized version. Why would they do that? Of course, you don't know why they would do it. Like, maybe there's at some point you could earn money on this thing, right? You could say, hey, I'm using my GPU and I want to be part of this training run, and people will pay me actually to make these rollouts. But actually, I'm gonna cheat. I'm gonna take the model weights that they gave me on the relay server, and I'm gonna quantize them. So before they used maybe 32 b float 16 for the weights, but now I'm gonna down quantize it to some 8-bit representation, and then I'm gonna do the forward pass. Then I still can get a rollout. It still looks reasonable and so on, but it's not as good. And it might mess up with the stability of the training and so on. So we do not want that. That would be we cannot just, like, even if we wanted to do it, we would all decide that this was being okay. So therefore, our top lock thing needs to say that this is not a valid reasoning rollout. And malicious versions of the model. So that's what we said. Like, maybe there can be some kind of thing where you try to generate trajectories that are weird, and in essence getting the final model to become, to have some behavior that that is like a backdoor or whatever. So sampling checks, termination checks. There are 2 valid termination criteria for generated sequences: reaching the model's maximum context length or producing the end of sequence token. So a language model is usually trained to have a specific maximum context length. That is aspects of, for example, when you have a rotational position embeddings and so on, you have specific parameters that kind of set a limit on that. But usually it's also more that the way that you trained it to work. So even if there's something about, for example, in rope, you have like a very high maximum theta base frequency thing, then it might theoretically have a long one. But if you never trained your model, your attention heads essentially to work with a longer maximum, very long documents, then you cannot actually get a good performance from it. So usually models will have some kind of maximum context length. Maybe it's 40K or something. And then there will be a specific token, the end of sequence token, which is a token like any other. When you're predicting the next token, you can predict that it's any word, and it could be that there's an end of sequence token, and then there will be the end. The way that the model is trained to use that is that it literally the training data that it has been seeing, the training process has inserted an end of sequence token in the very end, and it will also become part of the post training data. When you see the end of sequence token, usually you would put it in the end of the trajectory. So since longer sequences incur greater computational costs, inference providers may be incentivized to terminate sequences prematurely. So what does that mean? That means, like, let's say Bob, he's getting the model weights and everything, and he might be working in a setup where he's getting paid not by flops he uses or whatever, but he's getting paid for how many questions he can complete. And therefore he is saying, let me just generate, using the actual model, quite a long trajectory, but I'm somehow just gonna stop early. I'm just gonna artificially maybe insert the ends of sequence token. Maybe I try to do it in a like subtle way where I like gradually increase it when the end of sequence token is being slightly likely. Maybe if I have some specific sampling procedure for the inference rollout, at some point when the end of sequence token is becoming slightly likely, then I will like kind of prefer it, and I will just claim that it was I was just lucky that I didn't have to do a longer rollout. So this we cannot want. We want that the rollout should be kind of faithful to the actual model, so we agree. To guard against this, we check that either the sequence reaches the maximum model length or ends with an end of sequence token. That was not what I expected, because they could still do this. Of course, it might be hard to fake. I think the top lock hashing should protect against this thing. If you have the hidden states, in the final layer, and especially if you have some kind of deterministic greedy decoding, then you should not be able to fake it that well that you have an end of sequence. But it depends on your sampling procedure. But if we assume that, then it will of course be mostly important that we should make sure that either of these happen. Just basically saying, of course, no one can submit a sequence to the top lock validators that do not have these two, because then it's just not valid. In that case, that the sequence terminated on the generation of an ESC, we make sure that ES probably exceeds 0.1 to prevent manipulation through unlikely EOS generations. So that's what we just said. That we need to somehow check that it is likely enough that there is not a faking. Of course, it could maybe be a bit more robust, but that depends on the sampling procedure. Token sampling check. Proper sampling from logits should yield a distribution resembling an exponential with a mode of 1. So at 1. Yeah, so they're trying to reason about whether it makes sense to have it. Sampling from the logits should yield a distribution resembling exponential with mode at 1. So I think they mean that, like, consider the actual logits that you get in the end. The actual logits that you get in the end, these are of course used for sampling because you apply softmax and stuff like this. But if you just consider the logits, they will be maybe consider a single token. So there's the vocabulary is maybe 100k, so you have 100k values. These are logits. They can be technically any value between minus infinity and infinity. You are looking at a distribution over these logits, and they should be kind of exponentially distributed, they claim. But this will not be the case for other distributions. This is an interesting thing. I wonder, there must be some research in this area. Fixed data sampling. Allowing inference workers to choose their own samples could lead to cherry picking easy or previously completed examples. To run this, each node deterministically selects samples based on a seed computed as. Yeah, so they cannot choose their own ones because maybe they believe that some is easy and whatever. So this is maybe a number. Bob is number 7. Inference worker, and there's a step, and there's a number of submissions for this step. it's a number of submissions maybe Bob did. At least in that case, it would be some number that will just be out of its control. Then there's a seed. Then you put that through a random number generator, and you get an somehow a procedure that says now it's this question that you have to generate a rule out for. We then verify that the correct samples were used by reproducing the samples process from the seed. Yeah, so the top log or whatever can always like look when they say this is the seed, blah blah blah, that it actually matches the one if you have like a ground truth database over the data that you have to look at, the questions that you have to look at. Value bounds check. All reported scalar values such as rewards and events must fall within predefined bounds. Parquet formatting check. We also make sure that the Parquet has the correct schema and is in a format that is loadable by a training data loader. So Parquet is just a format, a file format wherein you will put what you need to put. You need to put some metadata, but most importantly, you need to put your trajectories. And you need to send that, and it needs to then go to the training loader, and they will use the data for training. So you need to check that. And all of this is in 2.3, right? Section 2.3. This is the top log. And I just need to understand, is this a separate repo or is it part of the RL? Top log. 2 months ago. Okay. Then there's a prime intellect protocol. The prime intellect protocol coordinates the permissionless nodes through a modular decentralized orchestration layer. It gives model trainers the ability to check the health of all nodes, view logs, and distribute new task analysis to a decentralized Slurm. So the model trainers are the managers. They are the ones who can say what they want to do. They can look at the health of all nodes and everything. So as shown in figure 4, the system, let's first just look at this plot, because now we understand illustration top log. The inference provider performs batched inference and generates commits for the computation performed. Inference provider performs batched inferences. Batched inferences means that you can actually take a batch of questions and you can generate tokens for all of them. Finding the top k indices and values in the last batched hidden states. That's their way of hashing, locality sensitive hashing. So then you're using a scheme where you are using a polynomial. This is very common in cryptography, where if you use that, you can use them as the coefficients of a polynomial. And no, you are taking the values, you're putting them at specific points, you're interpolating and getting a polynomial now that has certain coefficients. And these coefficients and the indices that you care about, they are now your feed. And this is a mathematics that, like, there's only so many polynomials, like there's a unique polynomial, blah blah, that goes through these points and so on. And then you will kind of be able to check extract exponent and mantissa bits from the values. So I'll just skip a bit of the technical things because it's probably existing elsewhere. And then you have verify processes commits up to 100 times faster than the time it takes the inference provider to generate them. So that's what we talked about. You can just do it in a forward pass. You are then doing the some kind of check, compute mantissa, error exceed threshold, / inference reward inference provider. So I still wonder how we think about the reward, because the inference provider could generate a right one but fake the reward. But maybe there's some thing going on here. Okay. They're implemented in Rust. All components except for the worker nodes and decentralized ledger are hosted in a Kubernetes cluster. So the worker nodes are, of course, like just hanging around. You and I could maybe be in the future easily be part of it, but some other parts are in the Kubernetes cluster. All API are protected by Cloudflare in order for like DDoS stuff. A decentralized ledger is used to store information about the current training run, ownership of the training run, as well as worker contributions. These workloads are organized into compute pools that belong to a broader compute domain. So this would be a bit like a blockchain kind of thing. It does not say exactly how it works. But you could imagine like that you have some kind of like ledger and everyone has to say like, okay, now I did these kind of inference, these questions, I made rollouts for those, and maybe the top log says like I verified this guy's stuff and whatever. So their workloads are organized into compute pools that all belong to a broader compute domain. Each compute domain represents a specific category of AI task: pre-training, synthetic data generation, distributed reinforcement learning, and so on. And then there are compute pools, workloads. The ledger maintains detailed information about each pool, including ownership detail and worker contributions. Each contributor, as well as the compute pool owner, has a cryptographic address used for signing transactions and proving ownership. Worker software. The worker software core task is to communicate heartbeats and metrics to the central orchestrator and configure and manage the local Docker environment for task execution. So there needs to be some software when you and I we host the weights and try to generate a trajectory, and maybe our model generates some code, and then the code should be executed maybe in Python, and then it should be checked that it verifies some unit tests and everything about that. It should be inside a Docker container so that it agrees everyone agrees on it, and there should be some kind of connection between the Docker container and the general worker thing that's running outside in Rust. The latter can be used to trigger actions on the worker software, such as file uploads from the Docker volumes. So you could imagine that there was some more advanced thing going on in here. Discovery service. The discovery service is a simple API that allows nodes to upload worker metadata information. So other authorized components to retrieve information about nodes that have signed up into a worker IP only. So why do we need to do that? The trainers, the orchestrators, the trainers are kind of like related to the orchestrators. They're the main guys. They are maybe want to know the IPs, but not everyone should know the IPs of you and me, as we are generating the rollouts. And this is some kind of API that is also discovery service. So that also means like, hey, I want to join, I want to do rollouts, so I can tell someone my IP. And since it's not fully P2P, it is like, yeah. So here is a protocol testnet infrastructure. So what was more fundamental, the pool or the domain? The domain was the important thing. So for example, the domain that we've been talking about has been some kind of distributed reinforcement learning. And then synthetic data generation is what they did yesterday and so on, with like the INTELLECT-2, where they just like want different people to generate So the rollouts are the synthetic data generations, but it's been separated now from the distributed reinforcement learning. So maybe they're thinking this is synthetic data generation in some sense, but maybe there is like a difference between synthetic data generations in the RL. Like it's why would you want to call the synthetic data generation when it's always that is always the case? Maybe synthetic data, like in this kind of RL, you're generating trajectories, rollouts. They are, of course, in that sense, synthetic. So that would always be involved in a distributed RL run, but you also have cases where you just have R1 or some other thing, and you're not doing online. You just want, say, DeepSeek's R1 to try that on a bunch of questions, and that is the synthetic. So, where were we? The ledger maintains detailed information about the pool. That was done here. Of tasks and observing the lifecycle of different workers based on their heartbeat. It gives the model trainer the ability to interact with the infrastructure via web API. It thereby exposes information about all nodes that are currently alive, an API to create and schedule new tasks, and insights into the current metrics. Since containers on each node might fail, each node work can be restarted. Node registry and discovery, the worker's software is installed and started by compute contributors on their machines. So you and I, we download some software, we install it, and then we're ready. It sees like, do I have an NVIDIA GPU or whatever? And that checks whether we can make use of that. And there might also be some systems that are just using CPUs. Maybe there's some advanced environments in the future where you just want to run a lot of code on or something. So additional software and connection uplinks checks are performed and inform the user in their logs about any misconfigurations. Once the system hardware are confirmed, the node automatically uploads its metadata. In parallel, the node also sends a registration call to the decentralized ledger. So there are two parts, right? The discovery service is like the centrally managed one. It's the one that can be used then by the orchestrator, can like look at what nodes are available and everything. But it also is like the decentralized ledger is somehow public. I guess it's not cryptographically encrypted information, so this is something everyone can see. After successful registration, the worker starts a web server and waits for invitation. this security measure ensures the workers doesn't need to know the orchestrator's endpoint in advance. So we're saying actually when we start, we will not know the orchestrator's IP. We know the discovery services IP, but if we hide the orchestrator and these are not hosted on the same server in a sense, then they can connect, and therefore there will be a protection there. The orchestrator periodically checks the discovery service for newly created nodes and sends an invite to the worker's HTTP server to start contributing. This invite contains a cryptographic signature combining the node's address as well as the compute pool's ID and domain. The invite is validated okay. I'm just gonna see here. I think I'm just gonna skip a bit on this protocol now. So this is the orchestrating discussion is acutely centralized, which simplifies coordination but creates potential single points of failure. This design also introduces trust assumptions that may not be suitable. To address this, we plan to move to more fully peer-to-peer architecture using a distributed hash table, which would eliminate the need for central coordination and enable more resilient decentralized node discovery. Another key limitation lies in how Worker is deployed. At present, it only runs on bare metal machines. The goal of INTELLECT-2 is to train a model with reasoning capabilities. In this section, we describe our RL recipe. I think this will be a second part now. I will stop here.